And we're live. Hello, world. We're working on LeetCode and taking on a hard level problem today. And let me share the screen. I guess I'm already sharing. So I haven't read the problem statement yet. I just saw that examples are like pretty long explanations, include pretty long explanations. Yeah, it's not the it's kind of intimidating, but let's see. Let me try and just maybe try to at least understand the problem and see if we can find the logical solution here within the next 20 minutes. Logic, 15 minutes. And code, within next, so 40 minutes. So find building where Alice and Bob can meet. You are given a zero index array heights of positive integers, where height ith represents the height of the ith building. Okay, so there's buildings with their heights. If a person is in building I, they can move to any other building J if and only if Ji is smaller than J and height I is smaller than height J. So that means I, so there will be I, then there will be J at some point, and the buildings are higher. So this is that building, and this is that building. Okay, so can move to any other building and a person in building I. Interesting. You are also given another array, queries, where queries I is an array with A and B. On the ith query, Alice is in building I, is in building A, where Bob is in building B. Okay. Return the array ans, where ans I is the index of the leftmost building, where Alice and Bob can meet on the ith query. If the leftmost. I thought you could only move from left to right, but they're saying well, yeah, the leftmost, so if Bob cannot move to a common building on query I, set ends I to -1. Okay, let's look at this example. We have heights 6, 4, 8, 5, 2, 7. And we have queries. Queries show, so Alice is in A and Bob is in B. So for the first query, A and B, in the first query, Alice and Bob can move to building 2. Since heights 0 is less than heights 2 and heights 1 is less than heights 2. Okay. Okay, so Alice is here, Bob is here, and they both can move here and meet there. Because 8 is bigger than 6. 6 is smaller than 8 and 4 is smaller than 8. Okay. Okay, the next query, 0 and 3. So that will be 6 and 5. And the second query to the building 5. Building 5 is 0, 1, 2, 3, 4, 5. So the 7. 7 is bigger than 6 and bigger than 5. Next query, 2 and 4. This is 2 and 4. There is no building bigger than 8. So, and Bob can but Bob is already in that building. So Bob can only move to that one. But Alice cannot move. Yeah, so Bob can move to but Alice cannot. So that's the problem. And well, and so on, 3, 4. So 3, 4 is again 5. Because they both can move to 7. And 2, 2 already in the same building. They're already in the same building. Well, what's the leftmost building where they can meet? And they only can, if they're not in one building already, they only can meet in a building where that's bigger and then to the right of their current building. Bigger than their current building and to the right. Okay, so let's think about a brute force solution. To kind of figure out what the brute force would be, we need to know, okay, how long is the heights? And then the height is already 10 to 9, to the power of 9. So And queries is 10 to the power of 4 multiplied by 5. Okay. Oh no, heights is also 10 to the power of 4. Okay, what does that mean? That means if we have n squared, we'll have 10 to the power of 8 well, actually 10 to the power of 9. So, because that 5 will also be... Oh, wait a second. Yeah, so that in the worst case is 10 to the power of 9. Interesting. So I'm curious about a brute force solution. Almond will help me. So simulation, which means we just do for each query, we'll do that search. Okay. I mean, the search is, you have 2 pointers. And you can start from the A and to the right and check if any of the nodes in the array, if any of the buildings is a good building for emitting. But we'll stop with the first one, with the leftmost. So that search is length m. So that sounds like ten to the power of 9 solution. Which is kind of long. So heights could be up to 1 billion. Wow, there are so many hints. So that's brute force. Can we do a bit better than that? By the way, that could be acceptable, but probably not. That could be. Now, what could make this go faster? I have a query. Zero and one. If we could say in constant time, we have 6 and 4. If we could say in constant time, values that are bigger I mean, obviously we check if they're in the same building. If they are, so we just move along. They're not in the same building. And by the way, B, it doesn't say that B is higher than A. Right? Or it does. So A and B is lower than this length of heights, but there could be any disposition. Okay, so we have 16 minutes. I think so far we have a brute force, but not an optimal solution. So what could we do in more of a constant time? Oh, this almond is irresistible. What could we do in constant time? Could we know for a given number because we need to take the biggest number out of these, right? And then tell, by the way, we need to return what? We need to return the buildings. So not just the fact that there is a building you can meet, but the actual indexes. Because, yeah, I mean, what can we know? If we go there a couple time or two, we can kind of learn the landscape. And we can kind of there is 50,000 buildings. on that street. So I'm talking about some memory, using some memory to doing that search faster instead of going over each building again and again. And so we might know, for example, for 6, we might know that there is 2 buildings that are bigger than 6 to the right. There is 8 and there is 7. We only care about 8 in this case. But, okay, 4, luckily, which is the smaller number, so it's automatically, but it also can move to 8 also, because it's before 8. So that helps, but but knowing there is a number but knowing there is a number to the right that's bigger, here is an idea. If we sort it and then do a binary search, then it's a different speed of search. Yeah. But in that case, we will mess up the order. Because only in this order, the index is smaller. But if we sort them, their indices will be all over the place. And I mean, we will have to iterate over them again and just try and see if any of them has a higher index. I mean, we can find the bigger value quick. Log n time, but then each of those higher values will need to check and go over them one by one. So that kind of doesn't, that is still kind of linear. Because this requirement, this condition, that it has to be, we can only move to the higher index building if j, building f, if and only if j is higher than I, and the height of the building is bigger. So yeah, that blocks the sorting and binary search. What else? What else? There is a billion up to a billion. These values, by the way, they're positive integers, so they're all from 0. How does that help? How is it helpful? Yeah. I'm trying to understand. Okay, we're 25 minutes in. And okay, we looked at the brute force. We thought about binary search. What else? I'm really not sure about the brute force. What else is there? Mm-hmm. Anything like some kind of dynamic programming, which means if we have solved the search for another number, could that help us? Or for the same number? Yeah, like for the index 0, the solution was at 8. But in the next case, since b is more than index 3, so that we can't reuse that solution. Unless we already have a solution for 4, or for 5, which is 3. So for 5, the solution, but for 3, the solution is this one. Is 5. Yeah, for 3, the solution is 5. And we have it already. But you see, it's these solutions are under condition for both A and B. So they might not be, they might not show us what this next pair requires. Might not be the right. Yeah, because each pair is different. So it feels like this binary search was a good like path. We just don't have we don't know how to solve it if the binary search doesn't work. Okay, another approach would be to try to still do the brute force And maybe we'll get some ideas along the way. Or there is still a little chance that the brute force will work. So for the brute force, we need to do the following. We will need to go over the queries. Queries. Now, I need answer. Oh, answer is a slice of integers, length, queries. So what we're gonna do? I'm gonna say that yeah. So we have our query, and now we're going to go over the we need to know which one is bigger. If V is, yeah, we need to know the, so first of all, if they are equal, if they're not equal, yeah, then we need to worry about it. Otherwise, we just, if one of them is bigger, we do the search from, we always do the search from the bigger one. Okay, and by the way, including that bigger one, yeah, starting from it. So if they're equal, we will append answer I is V is position, yeah. Okay, but yeah, now we just need to do our search depending on which one is bigger. Yeah, let's make a function which will be leftmost building, and it will get us, it will get the heights, And mhm. the positions, and it will return us the position. So yeah, if V0 is bigger, is smaller than V1, we'll say that pause is, and we call this leftmost building. And pass the heights, pass V1. Yeah, but what I meant was, yeah, if that's, yeah, if else if V1, I'll just articulate it here, just yeah, if it's the other, I mean, it's obviously the only option left. Yeah, then we'll have it the other way. Yeah. So this second value is bigger. Okay. So in this, we will go for range. We will go over the heights, but we actually not gonna just range over the heights. We're gonna start with B. With I is less than a length of heights, I plus plus. So we're gonna go over each of them, and we're just gonna if we find, yeah, else we return else. So else we return -1. If we never find anything, if we do find, we'll return that position. So now we look at this, is at this position. If heights I, so that's kind of this, that's some building, okay, and we know it's a building. Both of them, they could move because of it's to the right, but we need to make sure that if heights is smaller, or if heights is bigger than heights A, so that's a building A could move into. Now, I mean, if heights I is bigger than heights B, then return I. Yeah, but there is one case left here. And the case is, if it's the first building, which is B, so it's not gonna be bigger than it's gonna be the same building. But So if A could move there, yeah, let's put it. Yeah, if A could move there, smaller than heights. Yeah, if A could move there, if B, but that could be already enough. If B could move there, already enough if and I equals B, that's enough. Or so we have I equals B, or if I does not, so yeah, so B could also move there, one of these. Yeah, then return I. Yeah, so I think that's a brute force solution for this case. Leftmost building. When we call it, we don't need to pass the type. Yeah, we just need to call it. Ouch. So it says that the answers are wrong. So we're gonna go starting with the B, with the bigger, basically with the bigger index, whatever it is. And then the leftmost possible where both can move to. Okay, could it be could the problem be here? So position is initialized as -1. Yeah, if they're equal, if they're in the same house already, we assign that position is that, and answer, yeah, we move to the next query. Yeah, but if A is smaller, yeah, if B is bigger, yeah, we put it like that. If A is bigger, we put the bigger one there, yeah. And we get AB, and we start with the B, with the bigger one. Go until the end of, we need to go until the end of queries, not heights, baby. Oh, wait a second, heights, we need to go, yeah, sorry, we need to go until the end of, get all the heights, check out all the heights left, including the B, and if A can move into that building, and either the building already is already B, or the B can move, into that building, smaller. It has to be, yeah, so B can also move. We'll return that building. And we go over that. But if we never find a building both can move to, or return -1. Somehow we get zeros. Oh, I see. We need to check if they're equal. Yeah. Okay, so it worked the first. If they're equal, then we just return. Yeah. So there is a bug. This in the second case, everything was right, and there is. This 3, 0. So B is 0. 1, 2, 3, and 2 and 5. So we have 0 and 3. They can both move to 4. Oh, yeah. We need to worry about the index, not the yeah. Oh, wait a second. These are indices. Yeah. So these are indices. Yeah. The bigger index we pass. Yeah. The query. Yeah. These are the indices. Why would it return -1? So we have a case where B is bigger than A. So it's 3. Oh, wait a second. Oh my goodness. Jeez. I messed up this comparisons. Yeah, if A is bigger, if B is bigger, it's like that. If A is bigger, it's like that. Yeah. And we probably should, yeah. Okay, now let's see if it works for bigger test cases. Time limit exceeded. Yeah. Oh, gee, we're almost at the end. This test case. Yeah, we almost passed them, but this test case looks like it's 50,000 long. Yeah, time limit exceeded. Okay, we can work on it on optimizations, but we have something going that's already solved most of the test cases, worked on most of them. Now, yeah, for a bigger test case, we're looking for something that's not n square. And let's give it like, a couple more minutes and we'll make a summary. So what do we know? what do we know? We know that for each query, we do this search to the right. We do this search over this region, starting with the biggest index. And we just do it over and over again for each query, just checking each height, each building. But we could do better, probably. Using memory, I guess, somehow. Using memory. So typically what you do is you check out, you can use a hash map to get some data in pretty much constant time. You can, yeah, my neighbors are celebrating something. You can use we can save the solutions for the previous problems, or and yeah, we thought about it, but that wasn't too promising. And then the binary search with the sorted, when the data is sorted, which we also what do you call it? Which we also looked at and decided that it's gonna give us we can find the bigger number, the immediately bigger number, but in all of the numbers, that are starting, all of the numbers that are bigger, but their indices will be all over the place. So that is going to be, we'll need to iterate over those bigger numbers and check their indices down. That's kind of the challenge. And that sounds, again, like a linear solution, so which is pretty much the same thing. Okay. What else could be there? I'm just brainstorming. If we sort the queries, which are these pairs, if we sort the queries, that might be of some value, because like these are sorted by, these are equal by the A's, and sorted by the B's, sounding, but we still need to redo our search in the buildings because of this little difference. that makes us redo the search again. So, so it looks like, okay, in terms of the direction of in which we might find this optimization, it's probably around some kind of, it's most likely it's using some kind of dynamic programming, or it's using and by the way, let's look at the topics at least. Binary search, stack, binary indexed tree, segment tree, heap, priority queue, monotonic stack. Ooh. Why? How would you use a stack? How would you stack up? Okay. To summarize, okay, okay, it looks like if these are all the topics and we need to use a heap here, it's kind of a longer solution. I mean, stack is fine, but implementing a heap, at least in Go, I don't think there is a special method for it, so it will, at least I don't remember one. So it's not going to be interview format. So it does this problem look like an interview type of good problem for an interview. So it might not be if you need to implement a heap. I think so. I need to practice with the heaps more. I haven't been, but might not be good. It might be too long for an interview. Stack is fine. Binary search is classic. So how could you use a stack here? A stack will stack something up. So that will give us the values in the opposite direction. Stack, monotonic stack. So a stack that's not increasing or non-decreasing. Interesting. Well, so now as the next, okay, the summary is the brute force worked for almost all of the test cases. Okay, that's good news. And several questions we still have. Is this interview format? And do we want to take a little bit more time and solve it ourselves before we look at the hints? Okay. So I think I'll try to sleep on it. Maybe do a little bit more tomorrow or over the week, because this problem is from our Saturday LeetCode club. So it could be a good one to try to still solve myself without looking up the hints. So, well, that's kind of the hard problem in our random LeetCode on a fluke series. Thank you for watching. Like and subscribe, and we'll see you in the next video.